This is Algebra 2B, Statistics Lesson 3, Measures of Spread. So, first we're going to start with standard deviation. Standard deviation is going to be a data set's average distance from the mean. And it's telling us basically how clustered a data set would be around the mean, or maybe it's super spread out, right? Measure of spread, okay? And to calculate it for a sample set of data, we're going to first get the distance from the mean for each data point, okay? So that's each data point, the distance from the mean. Then we're going to take all of those values and we are going to square them. Then we're going to take all of those values and we are going to divide by, we're going to add them up. Remember our Greek sigma? We're going to add up all those numbers and then we're going to divide it by one less than the number of numbers. And then finally, we are going to square root the whole shebang. That's complicated. I know it's complicated. So I have some handy-dandy tables that are going to help organize all of that work for us. And I think it'll make some sense when we do that in the table. Okay? To keep going with our definitions, we have our outliers. Outliers are data points that are very, very far, significantly different from the bulk of the data. So we'll just say far away values. That is not a very scientifically, mathematically precise definition, but we're going to define our outliers as being greater than 1.5 IQR, interquartile ranges, from the interquartile range. And to put that in formula terms, we're going to take our lower quartile and we're going to subtract 1.5 interquartile ranges versus our upper fence. We're going to take our upper quartile and we're going to add 1.5 interquartile ranges. Okay? So if a value is less than the lower fence or greater than the upper fence, that value is far away. It becomes an outlier. I'm going to add a little bit more here about distribution shapes. So when we have a lower outlier, right? If you have a lower outlier, whether that is in a histogram or in a box plot, you're going to have number way down here, but then you're going to have the bulk of your data up here, lower outlier, right? So in a box form, he might look kind of like that, where you have a really long tail. Or in histogram form, he might look like a couple short boxes, right? But then maybe some, I didn't leave myself enough space, some like really, really tall boxes. See how it's kind of low and then to high? That's what a lower outlier would look like. And that kind of data is called skewed left, wherever the tail is. When you have an upper outlier, usually your data then will be the opposite, skewed right. So whether we are seeing that in a dot plot, a box plot, a histogram, we're going to have most of our data be pretty low, but then we're going to have one data point way up top, skewed to the right. In histogram form, that might look like a bunch of bars up here, right? And then maybe one. There could be some in the middle, but there's going to be one guy who's pretty far away from everybody else that is skewed right. Definitions out of the way, let's try an example. The table at right gives the points scored by Chicago Bulls players who played over 40 games during the 97-98 season. We're going to use this table to find the standard deviation. So first, xi. That is going to be each of our data values. So I'm going to copy these down here, 2, 3, 5, 7, 984, and so on until I get this whole table filled out, okay? The first thing we needed for our formula was we had to subtract the mean from each data point. So when I have my numbers, I need to find the mean of these numbers. 376. Okay, so bear with me. We got to add those all up and then divide by, is that 10? 11. Add those all up and divide by 11. So mean is sum divided by number of values. Our mean is 675. So this spot on the table is a place to record the mean, okay? The mean right here is 675. Next, we need the distance from each value to the mean. That's what this says. Take each number, subtract the mean, okay? So hopefully you get the idea. I'm going to pause it and finish this table so you're not watching me write a bunch of numbers for so long. Okay, I went ahead and filled in the next two columns. I did have this one wrong too, so sorry about that. I subtracted 984 instead of 675, the mean, right? So it should have been 984 minus 675 for 309. I kept subtracting 841 minus 675, 764 minus 675, each value in the first column minus 675. Then I kept going to the next column too. What we do here is take each of those answers and raise them to the power of 2. So this is 1,682 to the power of 2. This is 309 to the power of 2. 166 to the power of 2. Each value there to the power of 2. And what I like to do when I'm doing this, just to kind of make it a little faster, is if I was going to do, for example, this guy right here, okay, I would go 376 minus 675, and that's how I got the negative 299, and then square it right away. So I have that answer. It's a lot less typing to kind of zigzag down the columns like that. Okay, so step 1, get the mean. Step 2, subtract everything. Step 3, do everything to the power of 2. Next, we are doing the sum of this far column. So we're going to add up all the numbers over here, which looks like 3, 8, 4, 2, 0, 7, 0. 3,842,070. Next, we're going to calculate what's called the variance. To do that, we're going to divide by 10. So this says n minus 1. We're not going to divide by 11, even though there are 11 numbers. That would be the mean, right? Add them all up, divide by 11. We're going to do everything divided by 10, one less than the number of numbers, okay? So that's easy enough because all I got to do is drop that 0. Sorry, he keeps moving on me. Last step is to square root that number, okay? So I'm going to go square root of 384,207. and that gives me 619.8. Now that is a lot of work to show us that the average distance from the mean of these players is about 620 points. Now the thing about that is, hopefully we already noticed, we have one guy way up in the 2000s. I don't know if anybody's ever heard of Michael Jordan, but everybody else is in the hundreds. So that standard deviation is really high. What that tells us is that there's a lot of variability, but only because our average is really weighted. Okay, I'm going to go on to letter B, find the 5-number summary. The numbers I can see here are already in order. So I have my maximum and my minimum. And with 11 numbers, that means the 6th value will be the median. And if this is my middle point, I have 5 numbers on the bottom. So the 3rd number, and you can do the cross off if that helps to find the middle, will be my lower quartile. Cross off, cross off. That means 841 will be my upper quartile. So I'm going to list them in order. 167, 288, 416, 841, and 2,357. Calculate the outlier fences. Okay, we have these formulas right here. We need to input the quartiles into both of those fence formulas. So I know I'm going to be putting 288 and 841 into my fences. I'm going to go LF for lower fence is lower quartile minus 1.5 times the inner quartile range and the upper fence will be the upper quartile plus 1.5 inner quartile ranges. So everything else stays the same. Okay, let's go calculator. I have 288 minus 1.5, 841 minus 288. The lower fence is negative 541.5. What that means is any value less than negative 541 is an outlier. Obviously, we don't have any negative values. I don't think you can get negative points in a basketball game. So there are no lower outliers. Let's calculate the upper fence. And I'm going to just do that. And I'm going to go 841 plus. Everything else stays the same. That looks like 1,670. Anything greater than the upper fence is an outlier. So any value larger than 1,670 is an outlier. Guess what? Michael Jordan is an outlier. He's not just an outlier. He's like 600 points higher than an outlier, right? Anything that would have been 1,700, 1,800, 1,900, 2,000, those are all outliers. 2357 is definitely an outlier. Last one, create a modified box plot. So a modified box plot is going to look like a regular box plot, but rather than having the top whisker extend to an outlier, we're going to stop at the second highest point in the data set, the highest non-outlier, and then just show that there's an outlier. So I'm going to start with a number line. Let's start with 0, and let's go 1,000. And let's go, I'm going to try to evenly space this. Let's go 2,000, right? So that's going to be 1,500, 500, 2,500, okay? So my minimum was at 167. I was hoping I could get them all on the page at the same time, but I don't think it's going to happen. 167, that's like here. My lower quartile was 288. That's like here. My median was at 416. I know this line is 500, so I still haven't even hit the 500 line yet. Let's go 400 right about there. My upper quartile is at 841. It's going to be higher than 750, so maybe right about there. And my maximum was at 2357. That was 2000, so way up there. Now, a traditional box plot is going to have me draw a box around my quartile and then a line going down to my minimum. Since I'm making a modified box plot, I'm not going to draw the line up to the outlier. I'm going to draw a line up until 984, okay? Because that was my second highest point, my non-outlier. So I'm going to go up to 984, which is probably about here. And then I'm going to leave this way up at the top to show that there's an outlier there, but the box plot doesn't go that high. So you can see, second highest scorer, Michael Jordan, outlier. That's it. Good luck on the exercises. Please let me know if you have questions.